DDR1. DDR1 was the first generation of DDR memory to become mainstream in the early 2000s. If you imagine modern RAM as a highway, DDR1 was the moment computers went from a single-lane road to a two-lane road. It was simple, but it changed everything. It existed because older memory, called SDRAM, could only send data once per clock cycle. CPUs were getting faster, but memory wasn't keeping up, creating a bottleneck. DDR, which stands for double data rate, solved this by sending data twice per cycle instead of once. Think of it like a delivery truck that suddenly starts making 2 trips instead of 1 without increasing speed. The clock didn't necessarily run much faster, but more work got done in the same time. In real use, DDR1 typically ran between about 200 and 400 MHz effective speed. That was fast compared to SDR-AM, but extremely slow compared to what we use today. Back then, even 512 megabytes felt comfortable, while today, that wouldn't even load a modern operating system smoothly. Its biggest advantage was that huge jump in efficiency without dramatically increasing complexity. The downside was power consumption and limited capacity, which quickly became a problem as software grew heavier. DDR1 made sense for early Pentium 4 and Ath1 era machines, office computers, and basic home PCs of that time. Today, it's mostly relevant only for maintaining very old systems or understanding how memory evolved. DDR1 was like the first smartphone compared to flip phones. Not impressive by today's standards, but once it arrived, there was no going back. DDR2 arrived around 2003 as the next attempt to keep memory from slowing everything else down. At a glance, it looks similar to DDR1, but internally, it was designed to move data more efficiently while using less power. The reason it existed was simple. CPUs kept getting faster and needed more data more often. DDR1 was starting to become the new bottleneck. Engineers needed RAM that could feed processors faster without turning PCs into space heaters. DDR2 achieved this partly by increasing something called the prefetch buffer, which basically means it grabbed more data in advance before the CPU even asked for it. Imagine a waiter bringing multiple dishes at once instead of 1 plate per trip. Fewer trips, more efficiency. Speeds typically range from about 400 to 800 megahertz effective. That made it clearly faster than DDR1, but still modest compared to later generations. In real life, this meant smoother multitasking and slightly faster program launches, though not the kind of night and day difference people sometimes expect. The advantages were better bandwidth and lower voltage, dropping from about 2.5 volts to around 1.8 volts. But DDR2 also had higher latency at first, meaning some actions took slightly longer to start, even if overall throughput improved. DDR2 was ideal for mid-2000s desktops, early gaming PCs, and general home use during Windows XP and early Windows 7 years. If you were building a reasonably priced performance PC around 2006, this was your lane. DDR3 showed up around 2007, right when computers started shifting from simple single-task machines into true multitasking devices. This was the era when having dozens of browser tabs open started becoming normal instead of excessive. DDR3 was built to support that shift. It existed because DDR2 was starting to struggle with growing demands for multitasking operating systems, larger applications, and early solid-state drives. The industry needed memory that could move more data while also using less electricity, especially as laptops became more important. DDR3 improved efficiency by lowering voltage again and increasing how much data could be prepared ahead of time. Typical speeds range from about 800 MHz up to around 2,133 MHz on later modules. That made it significantly faster than DDR2, especially in bandwidth-heavy tasks. In practice, this meant smoother gaming, better video playback, and a much more responsive system when juggling multiple programs. The strengths were clear: higher capacity, lower power usage around 1.5 volts, and much better overall bandwidth. The main downside was that early DDR3 wasn't dramatically faster than high-end DDR2 in every task, especially when latency differences were involved. DDR3 became the standard for PCs through the late 2000s and most of the 2010s. It was perfect for gaming builds, student computers, and anyone wanting a balanced system without spending too much. DDR3 was the moment RAM stopped just keeping up and started giving computers room to breathe. Not flashy, just quietly making everything feel smoother. DDR4 became mainstream around 2014, arriving during a time when computers weren't just running programs anymore, they were constantly streaming, syncing, caching, and multitasking in the background. Memory now had to handle not just what you clicked, but what your system anticipated you might click next. It was created because DDR3 was reaching practical limits in capacity and efficiency. Modern games, creative software, and browsers were consuming more memory than ever. The industry needed RAM that could scale higher without dramatically increasing power usage. DDR4 improved performance by increasing bank groups, which basically allowed memory to organize tasks more efficiently and reduce traffic jams inside the RAM itself. Imagine replacing a single checkout line with multiple organized queues. More people get served without chaos. Speeds typically started around 2,133 MHz and later pushed past 3,200 MHz in common systems. Compared to DDR3, it delivered more bandwidth and better efficiency, though again, not every task saw massive gains. You'd feel it most in heavy multitasking, modern gaming, and content creation workloads. The advantages were higher maximum capacities, better power efficiency at around 1.2 volts, and stronger stability at higher speeds. The downside was that early DDR4 had higher latency than late DDR3, and upgrading required a new motherboard, which made transitions expensive. DDR4 became the default choice for gamers, streamers, professionals, and basically anyone building a serious PC from the mid-2000s through the early 2020s. Even today, it still offers a strong price-to-performance balance for budget and mid-range builds. DDR4 wasn't about making computers feel twice as fast. It was about making sure they didn't slow down as our expectations doubled. DDR5 started appearing in consumer systems around 2020, built for a world where workloads like 4K video, massive games, AI features, and heavy multitasking were becoming normal instead of niche. This wasn't just about speed anymore, it was about scalability. It exists because DDR4 began hitting limits in bandwidth and maximum module size. Modern CPUs with many cores needed more data at the same time, not just faster data. Memory had to evolve from feeding one hungry worker to feeding an entire team simultaneously. DDR5 changes how memory modules manage power and split internal channels so they can handle multiple data streams more efficiently. Speeds typically start around 4,800 MHz and continue climbing well past 6,000 MHz in consumer systems. Compared to DDR4, it offers much higher theoretical bandwidth, though in everyday use, the difference can depend heavily on the workload. Some tasks barely notice. Others, like large simulations or compression, definitely do. The strengths include massive future capacity potential, improved efficiency around 1.1 volts, and better parallel data handling. The downsides right now are cost, early adoption stability quirks, and the fact that not every program can fully use the extra bandwidth yet. DDR5 makes the most sense for high-end gaming PCs, workstations, developers, and anyone building a system meant to last many years. For basic use, it's often more about future-proofing than immediate necessity. DDR5 feels less like a simple upgrade and more like infrastructure for the next decade. Not just faster memory, but memory designed for problems we're only starting to. If this breakdown was useful, give it a like, subscribe for more deep dive tech content, and turn on notifications so you don't miss the next video.